Okay, 7.7. Now I've told you that I like sledgehammers. I like big, robust tools that handle everything. Today is the mother of all sledgehammers, because what we've done so far with integration is consider the cases where, after staring at the integrand for a while, can we guess the right technique that would work for that particular integral? That could range anywhere from just simple formulas to U substitution, integration by parts, trig integration, trig substitution, partial fractions, tables, computer algebra systems. You know, the CAS was a pretty good sledgehammer, right? Because it works, but a lot of times the answers it give us are so complicated and messy that even just trying to enter it into a homework assignment or writing it down on a piece of paper is a pain in the tuchus. Now, today we're going to do is not look at the larger problem of finding the indefinite integral. That's usually the more challenging one. The indefinite integral is the one without the limits, right? But finding a definite integral, which is basically just the problem of finding area underneath a curve. What's nice about that is all you really want out of that is a number. You want the numerical value of that area. Now, the only technique that we have as calculus students so far to get that number exactly is to find the antiderivative, right? That is, if I gave you an integral like this one that's sitting on the screen right here, integral from 0 to 1 e to the x squared dx, and said find that definite integral, your first step is to take any steps you can find to find that function whose derivative is e to the x squared. Once you find that, plug in 1, plug in 0, subtract, you've got the number. But there are two cases when we cannot find the definite integral. We can't find it exactly. We can't find the area under the curve. The first case is when we can't find an antiderivative. And actually, I don't even mean that we aren't able to, like we aren't good enough at our calculus. I mean, there are problems where there is no antiderivative. This right here is a perfect example. There is no closed form simple function whose derivative is e to the x squared. It doesn't exist. In fact, we've proven mathematically that it doesn't exist. So you cannot find that. Now, that doesn't mean that it doesn't actually have a value. This is a curve. E to the x squared looks something like this. It's steeper than a typical exponential curve, but if I go from 0 to 1 and I draw the area underneath there, we know that is some finite number. That number exists. So this mathematical object right here has a numerical value. It's just the fundamental theorem of calculus won't give us the answer. We don't have a tool that gives us that answer. We're going to have one today that gives us an answer. Okay? The other time that we don't have the ability to find the area underneath the curve is if we don't actually even have a formula for f of x. And you've not really seen many of those kinds of problems in here because I almost always will write down the integral of some formula, right? But there are problems in science and in mathematics and engineering where you have collected data. So instead of having a nice smooth curve, you've got data that came out of some kind of instrument, and it's measured this data over time. And what you want to know is what's the area underneath that curve. For example, if this was a velocity measure, you were measuring the speed of something at every given point time t, to find out how far it traveled, you would find the area underneath that curve, right? But the problem is you don't know the formula. So how do you find an integral if you don't know the formula? Well, today's technique actually lets you do that. Okay? What these cases will allow us to use something called approximate integration. That's the title of this section. You'll see this term in other texts occasionally. I thought I'd throw it at you anyway, just so you've heard it once before. If I say quadrature, it's a big fancy word that just means approximate integration. This actually isn't 100% new to you. You've done a little bit of this before because you've heard of the left-hand rectangle rule and the right-hand rectangle rule. You may have even talked about the midpoint rule before. We're going to do the midpoint rule. We're going to do Simpson's rule. If you've seen those before, then this is review for you. I'm not doing a whole lot new. I'm not even going to derive Simpson's rule for you, but I am going to talk a little bit about the errors and why one rule is king of all compared to the other rules. Namely, Simpson's rule is what we use. We basically use it for everything. Okay, so to refresh your memory, let's just start with the midpoint rule. I'm not even going to do the left-hand rule, the right-hand rule. So let's draw the picture of what I mean by the midpoint rule. I'm going to draw an axis. Let's say we start here at A and we're going all the way to B. What I'm going to do is I'm going to divide this up into subintervals, equally spaced subintervals. Okay, in subintervals. Which what that means then is that this, well, I'll measure right here, this distance right there, which I call delta x, would be b minus a divided by n. So that's a formula I'm going to use in all of these rules. I'm going to take and divide my interval from a to b into n equally spaced subintervals. So I'll calculate that number. Imagine now that I've got a function up here that I want to find the integral for. This is my f of x. First thing I do is I label these subinterval endpoints as x0 through xn. So I would call this one right here x0, which happens to be the same thing as a. I'm going to call this one x1, x2, x3, and so on, until I get all the way down to xn, which is the same thing as b. So this first interval from x0 to x1, what I'm going to do is I'm going to find the midpoint, which I'm going to call x1 with a bar over the top of it. By the way, it's actually very easy to find the x's because I'll just come over here to the right side and write that. x1 would be a plus delta x. x2 is a plus 2 delta x. You just keep adding another delta x each time to get the next value, right? So like this right here is a plus delta x because that's how far away that I moved. Okay, this would be a plus 2 delta x, and so on. So the formula that we typically will use is xi is a plus I delta x. When we do some examples, you'll see it's just a matter of repeatedly adding whatever your delta x is, and we use this formula here to get our delta x. Okay, now I need to get some of this stuff out of the way that I just wrote. I don't have to, actually. I'm just going to draw now. By the way, we need to talk about this x1 bar is the midpoint of x0 and x1. So how do you find the midpoint of 2 points? I mean, if I had two numbers, I wanted you to find the number that's exactly halfway in between them. Yeah, it's the average. Yeah, just add them and divide by 2. So x1 is like x1 plus x0 divided by 2. So that's this. And of course, x2 would be, with a bar over it, would be x2 plus x1 divided by 2, and so on. Just some helpful formulas that we'll use. Okay.
So the bar just means the mean.
Yeah. It's used in statistics for mean, for average, so that's why I'm using it here. That's the only one of these rules that has that extra point, and it's the point that's in between all of the x's. But the bar over the top means halfway in between. So now I go up from that point to the curve, and I draw a rectangle that's the height of the curve at the midpoint. And then I'd just keep doing that, right? I'd find a midpoint here, which I'd call x2 bar, and go up that high. And then I'd have another rectangle, and so on. So what I'm going to say is that the integral from a to b of f of x dx can be approximated by this capital M, which I'm going to let be the sum of all of these rectangles. Okay, M sub n, where n is the number of intervals. So let's think about this first rectangle that I drew right there. What's the area of that rectangle? Length times width. It's delta x times the height, which is the function at x1 bar. So I have a f of x1 bar times delta x. That's my first rectangle. What would be my second rectangle? Delta x. And then you just keep going, right? So you get all the way to f at x in bar times delta x. Okay? This is the sum of the rectangles. But notice then they all have a delta x in common, so I'm just going to factor that delta x out to the right and say this is like f of x1 bar plus f at x2 bar plus dot 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 plus f at xn bar. So just find your midpoints, plug them all into the function, add all those values up, and multiply by delta x. And now you have an approximate value for your integral. And the higher the n, you got more work to do, but the closer you get. The midpoint rule turns out to be a lot better than the left rule and the right hand rule, because when you look at the picture of how far off you are, notice this right here is like an overestimate, and then this right here is an underestimate, and they kind of cancel each other out, at least better than just starting at the left-hand side as your height of the rectangle or the right-hand side as the height of your rectangle. Okay, so here's how we apply the midpoint rule in general. First thing you do is you find delta x, then you find all your xi's, then you find all your midpoints, then you plug all your midpoints into this formula, plug your delta x in, stick that in a calculator, and you'll get a numerical approximation of your integral. Okay? It's easy. That's where the formula comes from, and that's all you got to remember. Notice, by the way, the coefficients here, I'll call my coefficient patterns is just 1, 1, 1, 1, 1 all the way. Meaning that there's just a 1 in front of here, there's a 1 in front of here, there's a 1 in front of here. That will make more sense when I show you what happens with the midpoint in the Simpson's rule, because you get different numbers in front. Okay, so with that, let's talk about the trapezoid rule. Okay, similar picture. Draw a vertical axis here. Draw a horizontal axis. Let's start with A. Let's end with B. Let's put a x1 here. We'll call that x0, x2, dot, dot, dot. Call this xn. Let's go ahead and throw in an xn minus 1 just to have it on the axis. Let's say that's my f of x. And the only thing we're going to do different now is instead of picking a midpoint and drawing up, what do we do with the trapezoid rule? We draw a trapezoid. We pick that point there. We pick that point there and draw a straight line. This dude right here,
They just happen to be even.
There's my trapezoid. Now it's worth remembering, if I have the trapezoids we learned about back in geometry, something like this. If the height of the trapezoid is h, and this down here is base 1, and this up here is base 2, we learn in geometry, actually even probably like 5th and 6th grade math nowadays, how to find the area of a trapezoid. Do you remember?
Base 1 plus base 2.
Base 1 plus base 2
Times the height of that.
times the height with a 1/2 out front. It's like the average of the bases, right? You take the top base, the bottom base. If you average those, find them in the middle, right? You get the rectangle that has the same size. Okay. So now in our case, this is like base 2, this is like base 1, and then this right here is the h. But now h is going to be delta x. Base 1 is going to be f at x naught, and base 2 is going to be f at x1. So then I can use the sum of all those trapezoids. Just repeat that process, right? If I drew another point here, went down, do another trapezoid there, and all the way through down to here, another trapezoid. All right, so the integral a to b of f of x dx would be approximately what I'm going to call T sub n for trapezoid. Keep in mind again, delta x is still b minus a over n. X sub I can be found by doing a plus I delta x. So you'll still use this. But now you're just going to add up all these areas of trapezoids. So let's do the first trapezoid. It's 1/2 base 1 plus base 2, which is f of x 0 plus f of x 1 times the height, delta x, plus second trapezoid, 1/2 f at x1 plus f at x2 times delta x, plus dot 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 1/2, I'll do the last one, which is f of x n minus 1 plus f at x n times delta x. You've just added up those n trapezoids. So that's where it comes from. You could do it this way, but actually it's a little simpler if we do a little bit of algebra work here. I'm going to take I'm going to notice that all of these have a 1/2 and a delta x, right? 1/2 delta x, 1/2 delta x. So I'm going to pull both of those just out front and write this as delta x over 2, and then write what's left behind. So I've got an f of x0 plus f of x1 plus, I've pulled the half and the delta x out of this one, so I've got f of x1 plus f of x2 plus, and so on. This last one's going to have a f of x sub n minus 1 plus f of x sub n all inside. And this is where something new shows up. Notice right here I've got 2 of those. How many f of x2s am I going to have? I'm actually going to have 2 of those as well, right? Because the next one is f of x2 plus f of x3, and the next one's f of x3 plus f of x4, all the way up to this one, which is going to have 2. But then there's only going to be 1 of the last one. So what this looks like is delta x over 2, f of x0 plus 2f of x1 plus 2f of x2 plus all the way out to 2f of xn minus 1 plus 1 of the f of xn's. Which should match the formula that we've got at the bottom of the page there. But again, I want you to notice what the coefficient pattern is. Because you don't have to memorize the formula, you really just memorize the pattern. You memorize the number that's out front, which is delta x over 2 for the trapezoid. And then inside you find all your endpoints, the x0, x1, all the way to xn. It's 1, 2, 2, 2, all the way out to 1. That's your coefficient pattern. See it? 1, 2, 2, 2. There's a 1 there. So to apply the trapezoid rule, you'll find delta x. You'll find the xi's using this. You don't have to find the midpoints at all with the trapezoid rule. And then you take Tn, which is this formula right there, and add it all up. Okay? So I did want you to see where those formulas at least came from if you had used them before. Now you've seen it once again. So let's actually do one. And these types of problems, you need your calculator. So if you don't have your calculator out, you'll want to get it out.
I swear I had it.
Follow along as closely as you can, but it will be good practice if you actually use your calculator as we go.
I can go get mine and be back in a few minutes. One of those right there.
Well, I'm going to keep working, so do what you want to do. All right. So trapezoid rule. First step with the trapezoid rule. I'm going to start with that one because it actually is a little bit less work because I don't have to find the midpoints. But we'll do both of them. We'll do the trapezoid rule and then we'll do the midpoint rule. So step 1, delta x. I don't want to do this in green. I'm going to do this in red. They tell us to find this integral using the trapezoid rule and the midpoint rule for n equals 5. Okay? So the trapezoid rule, first thing I do is I find delta x, which is b minus a over n. What's b and a in this problem? Yep, so 2 minus 1 over 5, 1/5, which I'm going to use a decimal. On these quadrature rules, on these approximate integrations, decimal. These are decimal approximations. Yes, in one form or another, yes. I may give you delta x and say go until your last value is a certain number, or I'll give you the limits and then give you n. Most of the time it's this way. But either way, you'll either know delta x or you'll know n, and from that is enough to find out what you're missing. All right, so let's start with our x's then. x0 is always your starting point, right? It's your a. So what is x1 going to be? It's 1.2. It's the next x. This is just 1 plus delta x. I'm going to erase this, but that's 1 plus 0.2. That's your delta x. A plus delta x. Okay? All right. x1 is 1.2, so x2 would be x3, x4, and x5 is 2.0, or just 2. Okay, so now plug this into the formula. T5 will be delta x over 2 of, remember that's f of x1 plus f, 2 f of x1, I said that wrong. It's f at x0 plus 2f at x1 plus 2f at x2 Notice it's a 1 in front of the f, 2, 2, 2, 2, and then the last one is just a 1 coefficient.
How far do you know how far to go? I'll just
Because we have to stop here. You just keep going till you get to the b. Yep, that's the only thing you need to know. And then like I said, you don't even have to count or know how many terms there are. You just keep going till you get to the end. And for your coefficients, put 1, 2, 2, 2, 2, 2, and then make sure that the last one that you do is just a 1. Okay, now in our case, we actually know what our f is, right? F is 1 over x. So notice, you don't even have to find the antiderivative. That's the beauty of this. You just need the integrand. So you've got now 0.2 over 2, because delta x was 0.2, times 1 over 1, plus 2 times 1 over 1.2, plus 2 over 1 over 1.4, plus 2 times 1 over 1.6, plus 2 over 1 over 1.8, plus 1 over 2.0. And the rest is calculator. And I got 0.69563, I'll go 6 decimal places, 635. So this is an approximation of the integral from 1 to 2 of 1 over x dx. Just as a side note here. But there's your answer. That's your trapezoid rule applied to that function. Okay? Questions about using the trapezoid rule? Again, this is like a sledgehammer. It's just a bunch of calculation, but the calculation gets you close. It's easy to do once you understand the formula. 1, 2, 2, 2, 2, 2, 2, 1. Right, that you're plugging into the formula, etc. But it's powerful. And you can imagine, if you were doing this on a computer, writing a code for a computer to do this is very automatic, because you're just telling the computer, find all of the endpoints, plug them into this formula, and calculate it for me. And there's easy ways to write code that does that. So now I can find the definite integral for any function, as close as I want to. Now, keep in mind, this word right here, it's approximation. It's not exact. If you want a more exact answer, what do?
add in more points.
Use a bigger n. Exactly. And if you want even better than that, use a bigger n. In a moment, we'll talk a little bit about how you choose how big of n you need to get the best possible approximation.
We can use this here for any integral.
Any definite integral, and as long as you realize that you're within some margin of error. This is not exact. And you won't get a nice formula out of this. So there are advantages to being able to actually find the exact integral, because it is then exact. But this works when you can't do that. This also works when you don't have the formula, when all you have are the function heights at all your endpoints, right? If all you have are the data heights, but you don't necessarily have an f to do it, you can still use this method. You just plug in for f at 1.2. Instead of plugging into a formula, you just pull the data out of the instrumentation that's giving you the data. All right, midpoint rule. The only difference now, we've still got delta x will be b minus a over xn, which is 2 minus 1 over 5, which is 1/5 or 0.2. You still got the same xi's up here, but now what are the midpoints? What would be x1 bar?
1.3.
Well,
Oh,
yeah, take those two. It's 1.1. It's the thing that's halfway between x0 and x1. I'm gonna write one of these calculations in, but the rest I'm just gonna write in. So this is x0 plus x1 over 2, or 1.0 plus 1.2 over 2. But you don't even have to necessarily do that, right? You can look at those two numbers and see what's halfway in between 1 and 1.2. So you don't necessarily have to plug into a formula as long as you can see what the midpoints are. But notice, you got to know the x's before you can find their midpoints. But I'm taking advantage of the fact that we already found them. Okay, so x2 bar would be 1.3. x3 bar between 1.5, 1.4, and 1.6 is 1.5. x4 bar is 1.7. x5 bar 1.9.
So now we didn't get to 2, so it's like that.
We didn't do what?
We didn't get all the way to 2.
Because we're in the midpoints now. If you go back and look at the picture on midpoints, we never actually plug in the endpoints. We go until we can't go any further. In fact, the way you know to stop on this one is you've actually found these x's up here and you've stopped. So you know that the last point's going to be the one that's halfway in between the last two. Do what? Right. You won't go past xn. In this case, xn is 5. You get 5 intervals. That's as far as you go. There's no interval past that to take the midpoint up. M5 is now just delta x times f at x1 bar, which is 1.1, plus f at 1.3, plus f at 1.5, plus f at 1.7, plus f at 1.9. Remember that the midpoint formula is just the sum of the functions. All the coefficients are 1, and it's just times delta x. So that's 0.2 times 1 over 1.1 plus 1 over 1.3. Remember, the reason I'm writing 1 over 1.1 is that's the function f in this case. If the integrand was something different, if it was sine of x or if it was cosine squared of x, you're plugging in these values of xi's or xi bars into whatever function is inside the integral. That's why I'm using 1 over the number. 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. Throw that in a calculator. And I get 0.691908. So again, that's an approximation. Now the question is, those are two different answers. Which do you think is better? Which one would we prefer to use? They're two completely different rules. Well, in this case, and the reason we're introducing this is that this is not always something we can do, but we can actually find this integral. This one we could check the exact answer and just see how far away we are. Okay? What is the integral of 1 to 2 of 1 over x dx? Can you actually do that integral? Natural log of x or log of x, just not ln of x. Natural log of x from 1 to 2, right? That's how we do it when we do the calculus of it. Fundamental theorem of calculus says find the antiderivative and then plug in the limit. So log of 2 minus log of 1. Log of 1, by the way, is 0. What do I have to raise e to get 1? 0. So log of 2. Plug that into your calculator. What do you get? 693. Let's do 6 digits so we can compare to these guys up here. 147. And it keeps on going. It's irrational. But now we can look at how well we compare. So to 2 decimal places, we're good. The real question is, can we measure the error, right? And so I've thrown in a couple of formulas in that you've probably seen somewhere before in either math or science courses. Just to remember, the concept of absolute error means take your approximation, subtract your actual value, and take the absolute value of it. I'm going to call this like E. I might call it E sub T, E sub M, later on E sub S for Simpson's rule. And you can also calculate what's called relative error. I don't want to go through the details of that too much. In fact, I'm not even calculating relative error. For now, let's just talk about absolute error. So we can compare absolutely which one was closer, trapezoid rule or midpoint rule. So when I say E sub T, I mean the absolute error, and this one's the trapezoid rule. So what was the approximate value we got for the trapezoid rule? 635 minus the actual value, which gives me 0.002488, and E sub M, which would be the midpoint error, is the absolute value of 0.691908, right? Minus 0.693147, and I got 0.001239. So which was better? Midpoint. A little bit surprising that it is. Now, trapezoid is almost always better than left-hand rule and right-hand rule, but midpoint turns out to generally be better than the trapezoid rule.
The graph of 1 over x is just
The 1 over x looks like
Or am I thinking?
this. So if we're going from 1 to 2, okay?
I'm thinking the wrong graph. It's like that makes no sense. I'm thinking of absolute.
Now here's what I did. I went ahead in Excel
Absolute values.
and I went and calculated all of these for different values of n, just so you can stare at this for a second. So what I have, the top table here has different values of n. N equals 5, n equals 10, equals 20. And horizontally, I've got a column for the left-hand rule. And left-hand rule just means all the heights of my rectangles are measured at the left side of my subinterval, right? And that gives actually a pretty big gap in most cases. And you do that all the way on the left-hand side. And then the right-hand rule can't write today. Right-hand rule. This was trapezoid. And this was midpoint. And so, like, the values that we got were right here. No. Right here. You recognize those? So if I did the left-hand rule and right-hand rule, I got something far worse. And we're trying to get close to 0.693147. So I tried it with 10 subintervals, and then I tried it with 20 subintervals, and I calculated what I got. And then I measured the absolute error for each one of these. So like this corresponds with this one right up here. What was the absolute error for the left-hand rule with 5? It was 0.05. The right-hand rule was 0.04. Okay? The trapezoid rule, that's what we got, was 0.002488. And for our midpoint rule, we got 0.001239. So notice as you go along this way, which one is better in every case? Midpoint. There's a theorem that we won't get to prove in here, but if you want to know why, then you should take my numerical analysis course the next time it's offered, because that's what numerical analysis is all about. Numerical analysis is the math of approximating solutions. It's not necessarily deriving the techniques like we've done today, but it's proving these theorems as to how accurate are my approximations. It's fun stuff. It's my field. I'm a numerical analyst by training. That's what my PhD is actually in. What this theorem down here tells you says that both of these things, the error of the trapezoid rule and the error of the midpoint rule, get small as n gets large. We know that. That's kind of what we expect. But this formula tells me how fast it gets small by how fast n gets large. And the key variable here is right there, or the key parameter. Both of these have what's called an n squared, or a 1 over n squared approximation order. What that says is that as I double my number of n, if this had been just like 1 over n, n to the first power, then doubling the size of my intervals, or doubling the number of intervals, would cut my error in half. But this is n squared. So what that says is that if I double my number of intervals, then my error is cut by 1 over n squared. 1 over 2 squared, that is, I'm doubling, so it's twice as big. So now it's half squared, which means it's a fourth the amount of error. Doubling the number of intervals will cut your error by a fourth. And if you look at that, that's exactly what appears to be happening as I go from here. I went from n equals 5 to now n equals 10. As I went from here to here, same thing here, this is my error. Notice my error, since I doubled my number of intervals, was cut by about a fourth, right? 0.6 is a fourth of 24. It's beautiful that that just shows up exactly as you would expect according to this theorem down here. And the same thing even happens right here. I doubled my number of intervals, but my error went down by a fourth. Roughly the same thing again. A fourth of 32 would be 8. So that's pretty close. Pretty close to being cut by 1/4. Factor of 4. Okay? It's beautiful. Beautiful. But notice in the theorem, the real difference between the midpoint and the trapezoid, since they both converge at the same rate, the only real difference is this constant here, which I can't tell you quickly where that comes from. I can only say that the midpoint has a bigger number on bottom, so its error is smaller. And it's always smaller. So midpoint's better. But nobody would really even use the midpoint rule in practice, because there is a better rule out there. There is the Simpson's rule. And to be honest with you, there are actually several Simpson's rule. I'm going to give you the first. This was actually sometimes called the 1/3 Simpson's rule. There's a 3/8 Simpson's rule out there. The idea is simple. And I can't derive it for you, but think of it this way. I mean, I can, I don't have time. You've got a function, f of x. This is your x0, x1, x2, maybe this is x3, x4, dot, dot, dot. So here's what we do with Simpson's rule. We don't form a polygon like a trapezoid or a rectangle. We form a parabola. We take 3 points, group these two subintervals together, and we fit a parabola to these 3. Why a parabola? Well, 2 reasons. Parabolas have this equation right here. Are all ax squared plus bx plus c. How many unknowns, how many parameters are there in a parabola? There's an A, there's a B, there's a C. 3 unknowns. X is the variable, so it's not considered the unknown. It's the function of the variable. It's the independent variable. But you got 3 things, 3 numbers that describe a parabola uniquely. In order to describe a parabola, you need 3 pieces of information. One way to do it is you need 3 coefficients. Okay? Well, with 3 points, I can now find a specific parabola that goes through that point, that set of points. With 3 points, I can find the parabola that fits it. The second thing that's good about a parabola is it's easy to find the area underneath. Once you know what the parabola is that fits this, say this parabola looks like this. Boop, 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 boop. It's this giant big parabola this way. It doesn't match the red exactly. There's a little gap in there, but it's this giant U that fits right onto that set of points. Then integrate that parabola over that interval, find the area, and then do the same thing for the next 3 points. Use this one, and this one, okay? And then repeat. And ... we can derive
So
a formula.
when you derive the next 3 points, do you have to use the last point that you used?
Yeah, you use this one, and this one to get another one. So you have a parabola that goes right here. But all you do is you find the area underneath that parabola over those 2 subintervals. And then you just repeat that. That's how you derive Simpson's rule. And he actually goes through this in the book if you want to pull up the ebook and look at it. But all of the work eventually ends with a very simple to use formula. Looks just like our midpoint formula in that you've got a coefficient out front, right? This is the reason it's called the 1/3 Simpson's rule is it's 1/3 delta x out front. Okay? I don't know what I was going to label that, so I'm going to erase that error. I think I used green for this before. But notice the coefficient pattern is 1, 4, 2, 4, 2, 4. And it keeps going, but it'll always end with a 4 and then a 1. Okay? The one criteria for Simpson's rule to work is that n has to be even. Why does n have to be even? Well, it's because we used 2 subintervals to make each parabola. So we always have to end on an even number to be able to have a parabola on our last 2 subintervals, okay? But as long as n is even, you'll be able to use this coefficient pattern. So the process is exactly the same as for the trapezoid rule. You find your delta x, you find your xi's, then you plug them into that formula right there. Okay? I'm out of time, so I'm going to stop there, but I'll post the notes for this. Last thing I want to show you is this table on the final page. Look at that table. If I actually did calculate, and the example I'm doing is 10, I got 693,150. Look at the error. It's very fast to converge to the actual area. So people in practice will almost always use Simpson's rule, either the 1/3 Simpson's rule or even higher order Simpson's rules to get their answer.
So is there a difference Simpson's rules?
No, you always have to have an even number. So you just got to decide ahead of time. You're going to do an even number of subintervals to use Simpson's rule. If you don't have an even number, then you throw one number out.
So
Stop short.
Is it error right there where it's one space because it's 5 and it's 5?
Yes, 5 is not an even number, so I can't apply Simpson's rule right here. So I couldn't compare it directly. I could try maybe n equals 6. If I did n equals 4, I actually get a better approximation than even the midpoint rule at 5.
It's terrible.
It's that much better. All right, I'm done. 7.7 homework is available, I believe. If not, I'll make sure it
Now,
is.
the practice problems that we had to lab.
Yes. No, they do not count towards your average.
Let me get the
This I do.
notes.
I put them all up. Okay.
No, I went back there.
About the focus.
Somebody must have grabbed two or something.
There's a bunch of us yesterday that completely forgot about task corrections. Will they do last night, so they do it?
They were due yesterday. Can you get it to me today?
Yeah, I'll have them right now. Look it
Go
up.
put them in my box.
Okay.
I can print you off a copy back in my office. I brought 11 copies with me, so somebody had